Okay, we've got a shape bounded by these curves. Now we're going to get to moment of inertia, mass, density, put all that together in this example. Because of course what's coming up is we're doing it in 3 dimensions, which just means we've got one more dimension to worry about. But the principle is going to be the same. So first you got to graph these things. Now, graph these things. Y equals x squared is just your basic parabola. Okay? Turn it upside down, and you got negative x squared. Raise it up 16 units, and you got 16 minus x squared. Okay? So this is just, I'll just draw it real. Got this basic y equals x squared parabola. I can draw very well. And you turn it upside down. And then you raise it up 16 units. And there you got it. So sufficient to this problem, you put 16 up here, and you figure out what your y-intercept is. Well, that is your y-intercept. Figure out what your x-intercept is, let y equal 0, and you get x equals 4, or negative 4. Okay? That's how you want to do this graph. Okay? You don't want to plot a bunch of points. You want to look for the intercepts. You want to use pre-calculus techniques. Okay, then you have x plus y equals 5. It's a straight line. Identify that easily as a straight line. And it's got a y-intercept of 5 and an x-intercept of 5. So you don't need to plot points if you know what the shape of the x squared graph is, which is one of your toolkit functions you learn about in pre-calculus. And there you have it in straight lines. Well, straight lines, that's algebra 1. Okay? Go by the intercepts when you can. Otherwise, go by the slope and the y-intercept. You got the equation of the line, you can do one of the two. Okay. So now it's bounded by this. Well, that's going to be this region here. Now you want to set up your integral. You're either going to set up the integral on an x interval or on a y interval. You're going to do x cross sections or y cross sections. So I'm going to do it with x cross sections. We also have to do it with y cross sections because you've got problems that ask you to change the order of integration. Okay? So we'll talk about that a little bit too. So here we have an x interval over which we can integrate this thing, right? And we're going to think of, okay, we're going to partition this interval. We take a typical partition. We're going to get a y interval. We're going to have a sample point. That'll give us a rectangular region here that we can then partition with respect to y, which is why we do the description the way we do. Of course, we've been over that quite a bit. So you always want to think about this. There's no magic bullet. You just think about the picture of what you're doing. Okay, so it should be obvious that we need to find this intersection and this intersection. So we have intersection of the curve. Well, y equals 16 minus x squared and x plus y equals 5. implies that x plus 16 minus x squared equals 5. Well, that's a quadratic equation, quadratic in x, so we pretty much, okay, on a calculus test, you might expect that it's been set up nicely so you can factor the thing. Since we're taking a quick look to see if you can factor it, you can always use a quadratic formula, and that's what I'm almost certainly going to end up doing because I gave no thought to making this factorable. Right? So that equation can become x squared minus x minus 21 equals 0. Okay. And you're not going to factor that. The factors are 21, 3 and 7, or 21 and 0. 21 and 1, 21 and 0. Okay. So now x is either 1, well, it's 1 plus or minus square root of, and I'm not going to go through the details. You're going to get 1 squared here, which is 1, and 4 times 4 AC is going to be 84. You're going to have a square root of 85. Okay. Now, usually, you know, in a lot of homework and stuff, it'll be set up to get nice numbers here. But now we know what the interval is that we partition. So we have 1 minus the square root of 85 over 2. And of course, square root of 85 is a little more than 9. 1 minus 9 would be 8 over 2. Would be negative 8. Divide by 2, you have negative 4. So that's around negative 4. But it's not quite negative 4, and it's really should be all that close to negative 4. Next, I'm getting something to the left of negative 4, which means I probably did something wrong. Okay? So let's see what I might have done wrong. We got 16 minus x squared. So I change the signs of everything, so we have a leading coefficient of 1. That gives us a negative x. And we subtract 5. Oh, whoa, there it is. Okay. I lost track of the sign there. It's going to be negative 11, not negative 21. I'll make that 45. The square root of 45 is a little less than 7. 1 minus 7 over 2 would be 3. A little less than that is a little less than 3, so that makes sense. You know how it helps to have a good picture. Okay. Now, if you're using technology, you can always get a good picture of the graph, but you don't get much understanding out of that. Depends on how many of these things you have to do and how good you are at doing them. You always have to be able to do it, I think, by hand. I mean, you should be able to slot down that graph quicker than you can construct it on a calculator. You know, on more complicated functions, you got a elliptic function or some crazy thing. Yeah, you won't have a clue how to graph it. That's when you go to the technology, right? Or if you really always know how to do this, you can visualize the thing. Well, you got to use your own judgment. I think I've said that at UVA, when they were setting up the whole engineering program thing, went to some meetings, and they said up there that their students never touch a calculator until their junior year, and then they never do anything by hand. Okay. I think that's a really good philosophy to take. Okay. I do not personally support any use of calculators except for doing your basic arithmetic until you know how to do all this stuff like that. Okay, well, anyhow, you know, there are some good investigative applications that you can do, but it gets out of hand and people use end up using the calculator's approach. So make sure we know how to graph, make sure we know how to transform functions, shifts, and stretches, okay, compressions, even rotations, but that's a challenge. Well, enough editorial comments. We got this, and it's a square root of 45, not 85. That completely there it is. And this is 1 plus square root of 45 over 2, which is kind of like 1 plus 7 over 2, which would be 4. But the square root of 45 is a little less than 4. And that shows you that you're pretty close to this intercept here when you intersect. When the curves intersect, it's pretty close to this intercept. And graph isn't completely right, but I've got the intercept marked here when really my curve intercepts over here. Okay, so there's a pretty good picture. You really want to understand details like that. And think about the arithmetic, make sure everything's consistent before you go committing yourself to figuring out the center of mass or the moment of inertia of this thing, sending it on to the engineers who are going to design it and make it work. And then you find that everything falls apart because you weren't quite careful enough, right? Yep, it's like you're an engineering team. And this is your responsibility passed on to somebody else. And they believe you and you made a mistake. Now, any good engineering team, they're going to be redundancies. That's what I said. You don't want to be the guy that makes mistakes. For a lot of reasons. If you're committed to the project, you don't want to make a mistake. You want to keep your job. You don't want to make a lot of mistakes. When you get a promotion, you don't want to make mistakes. Okay. Well, I'm just stalling. I don't know how to do this. We intersect these curves, right? So what do? You don't have to actually write this out every time, but I will probably ask you to write it out. It's no problem. Okay. We'll get the testing on this. You partition. There's your partition, and that's going to tell you what the limits on your x interval are. It's actually, obviously, when we integrate with respect to x, we integrate from here to here. Then, for a given y strip, what interval do we partition? Well, if this is xi star here, we'll label it there, but there's your xi star. Then your y value goes from this curve to this curve, right? Okay. So if your sample point is xi star, pretty obvious what your y interval is. Y equals 5 minus x, right? In other words, on this straight line, y equals 5 minus x. So it's five minus xi star less than or equal to y less than or equal to 16 minus xi star squared. Okay. Hopefully this is starting to take in, not trivial. But it's kind of always the same, it just has different functions. So then you partition and once you've partitioned it, you have your typical interval. And I didn't write the typical interval in here. But the typical interval, the typical increment is that's on minus 1 less than, we'll do less than x, less than or equal to x pi. I'll square that. A little sloppy, but that way. The sample point xi star. So that now, when you get your y increment, you're going to have a y j minus 1 less than y less than yj. Sample point yj star. Okay. Now, if we want to just get the area, well, rectangular increment, it's delta xi by delta yj. Total area is approximately that should be a YM over the end there. There's your total area. You just add it up over all your increments. And then by limits, and again, recommending that you didn't see how the limit works in your calculus course, you get a good reference. Okay. I'll do it right now because those should start to the midterm. This isn't on it, but stay up with this in the meantime, okay? But then in the last phase of this course, solidify your understanding what an interval is, okay? And how this process gives you the interval, because that's the process you've got to think through to do moment of inertia calculation, volume calculations, that's not the mass calculations, and so forth. But we're going to get all that in this example. Then we're going to do some 3 dimensions. Okay. So total area is this, and that approaches an interval. And the interval goes from what to what? Well, your first integral is going to be with respect to x because, well, your outer integral would be with respect to x because your limits on x are just numbers. Okay, you don't want your outer integral to be y because the limits on y depend on your value of x. Okay, because we chose to integrate this. With through vertical strips. Okay. Okay, so this is going to be 1 minus the square root of 45 over 2. And now I'm worried about the watermark. Oops, so a little bit. Not so far to see everything up. Okay, and just up to the square root of 1 plus the square root of 45 all over 2. And then that's with respect to x. What do we integrate with respect to x? Well, we integrate with respect to y from 5 minus x up to 16 minus x squared. There's the integral for the area of this thing. So let's go ahead and calculate that. Now, if we have a density function, it becomes really easy to set up the integral for the mass. Or for the moment of inertia about any line we might want to construct. And let's go ahead and do the integral over here. So well, antiderivative of 1 dy is just y, right? Okay. So that's going to be evaluated from 5 minus x, 16 minus x squared, and then that'll be integrated with respect to x. Well, it's kind of neat how this works out. Quickly becomes obvious why it does. But when you substitute 5 minus x and 16 minus x squared, evaluate the integral here, you get 16 minus x squared minus the quantity 5 minus x. I'm not going to write out a whole new step to do the minus quantity 5 minus x. I'll just kind of note over here we got negative x squared plus x plus 11. If I did that right, let's make sure you got a negative x squared, a minus minus x gives you plus x, and 16 minus 5 gives you 11. So it's clear that the antiderivative is going to be negative x cubed over 3 plus x squared over 2 plus 11 evaluated between 1 minus the square root of 45 over 2 and 1 plus square root of 0.5. Now, at this point, there isn't a whole lot of justification in most cases for doing the algebra for the exact calculation. Okay. So at this point, we can approximate this square root of 45. It's going to be about 6.7. Maybe even a little less than 6.7. I think 6.7. So that 1 plus 6.7 is 7.7. 7.7 divided by 2. That works right out. Down here, you're going to have 5.7 divided by 2, right? And negative 5.7 divided by 2. And that's negative 2.85. And up here, it's going to be 7.7 divided by 2, which is going to be 3.85. And they should differ by 1 because you have plus that right 1 minus. Hold on. 1. Okay, I think that's right. I mean, if it isn't, do your calculator. Okay. Not gonna be labored. And I'm going to say, stick my neck out and cube these things. Of course, 4 cubed is 64, 3 cubed is 27, so that's probably about 50. Okay. And that just goes. And that's going to be somewhat less than 27, so that's negative 20. Okay. So that's 53 and that's negative 25. And this is cube. Difference about 30. 30 over 3 is about 10. Check. Okay. Could have set this up carefully with nice numbers. See how it works out. Check my. That's got to be that. That is plus x squared over 2. We just approximate that as 16 and 9. That's like 7 halves. And that equals 4.5. Which I kind of don't believe for a minute. It's much more than that. So something's wrong. Yeah, and what's wrong is even wronger. That doesn't fit the picture. That's something. Tell me when we integrate 11, we get 11x. Thank you. Okay, that's going to help a lot. Because now 11, well, 3.85 minus negative 2.85, okay, is like 6.7. That times 11 is maybe 75. And that comes out ballpark 80. Now, is 80 a good approximation to the area? Does 80 make sense in terms of the area of this figure? Well, first of all, this is 16 up here. And the width is 8 if you take the whole part of the parabola above the x-axis. So a rectangle enclosing this thing would be 16 by 8 with an area of 128, right? Now, you're losing some of the area, but you've got most of the area inside an enclosing rectangle. I'm going to say that total area is maybe 100. If you cut the thing here, that means you got the upper half. That's less than half the area, so I don't like 80 much either. Okay, 80 is a little bit high, but it could be in my numbers there, and there's a very good chance of that. I like, okay, no. Well, I don't see it. If you run the numbers, it should work. Find another thing. Yeah, but not when you integrate it. You do get 11x when you integrate that left. Wait a minute. Let's pause this thing and reconcile this. Yeah, well, we just identified also that when I made that 75 estimate, I left the 11 in there. Of course, the 11 isn't there anymore with 11x. So it was the 75. That puts it closer to 12.70. It's still too much, but let's move on, because you can always use your calculator and do the arithmetic, right? Assuming I've done everything else. Okay. Now, let's say that we want to find the area, which we kind of did. Let's find the mass. If the density is we don't want to get a negative density. So we'll just use a simple density function like y plus 2x squared. Now, what's that mean? How does y plus 2x squared vary over this region? Well, the higher you go in a vertical strip, the bigger y gets, right? So in each one of these vertical strips, you have an increasing density, which means if you partition this into equal y intervals, each of these intervals is going to have more mass than the one before. Okay. Now, 2x squared has even more effect. Of course, when x equals 0 on the y-axis, you have your minimum density, which is just going to be y. Okay, it's going to go from 5 to 16. Okay. When x equals 1, then x squared would be 1. Okay. And you'd have y plus 2 on vertical strip at x equals 1. By the time you get out to x equals 3, x squared is 9, 2x squared is 18, and it's going to be 18 plus y, so the 2x squared is going to have more effect on the density than the y value. Okay. Because of course, out here the y value doesn't go, well, y doesn't go all that high. The closer you get out here, the more restricted the value of y is. The lower the upper bound is on the density. So you're going to get kind of a feel for it. Okay. You could even look at a shaded diagram where the color changes, gets more intense as you go up. Okay. And then as you go to the right, the color kind of follows this, but then it starts really getting much denser. Okay. The color gets much brighter or much more saturated or whatever. That makes sense? And of course, you use blue and red, blue for low density, red for high density. And go from blue to red along the spectrum. So you can represent the density in a visual way. So I'm going to think about how that is done and what that would look like for this function. Now, it is going to be symmetric because of the x squared. It'll be symmetric with respect to the y-axis. But the region itself isn't symmetric with respect to the y-axis. So, and how you're going to get something, and you can make an estimate. I mean, the maximum density is probably going to occur somewhere along here where x squared is about 4. Okay, x is about 4, so x squared is about 16. 2x squared would be about 32, right? And out here, the y doesn't look like it goes up much more than 4 or so. So your maximum density might be around 36. Your average density between here and here goes from 5 to 16 linearly because of y when x equals 0. So its average density here is going to be like 11 and a half, 10 and a half, whatever. 5 to 60, 20, 10 and a half, right? So density goes from like 10 and a half here, like 32 out here. But it rises according to the square between here and here. So it stays kind of close to what just y would give you. And then it goes up more rapidly when you get out here because the slope of the x squared function and stuff, which doesn't have anything to do with the shape of the region. Okay, so you can estimate, let's keep ourselves honest, that the average density might be in the maybe mid to upper teens, okay, over this whole region. If the density was 15 and the area was 40, it's kind of what I think it is. Okay, that's something in the 40. If the area is 50, then your total mass would be about 750. Average density of 15 multiplied by an area of about 50. 15 times 50 is 750. If the density, average density is 20, and it's not that high, it could be closer to 15 than 20, but somewhere in that range, then you'd have 1,000. So I'm expecting that the integral for the mass of this thing is going to be somewhere around 750 to 1,000. Okay. Now, do you kind of understand what I'm saying there? I mean, I'm just looking at how this density function changes from minimum of 5 right here to maximum of probably somewhat a little over 32 or somewhere in the maybe mid 30s at some point out there. And I know then if the area of this thing's like 50, that the total mass is probably not going to be less than 11 over 50, 10 and a half times 50 would be 500. It's certainly not going to be more than what you get for a density of like 30, which would be 1,500. So if this integral doesn't come out between 500 and 1500, that raises a red flag. Well, let's go on with the integration. Okay, now, try to put this here. Density function, and we'll use sigma. We usually use sigma for an area density, lambda for linear density, and rho for a volume density. But rho might be inconvenient in this course because a lot of times we're doing these things in spherical coordinates. We rho is linear spherical coordinates. So what we use there kind of depends on what coordinate system we use. But here the density function, sigma is saved. It's pretty clear. To get the mass, you just multiply the density by the area. Okay. Then total mass will be approximately the sum minus 1 to m, K equals 1 to m of yj star plus 2xi star squared delta xi delta yj. That approaches the integral. And the integral is going to have exactly the same limits it did before. So we just, this is obvious. You understand what density means. And key thing is, you look at the typical increment. Once you know what the quantity you're looking for is on the typical increment, at least what it, how we approximate it on the typical increment before we shrink all the increments down to nothing. Once you know this, it's really easy to write out this and this. Okay. Now, eventually, you get to the point where you think on that tree and say, yeah, well, all we're going to have to do is we're going to have to put that density function in right here. You don't want to skip these steps until you use the think through. You don't necessarily have to write them out every time. Discipline yourself for thinking through. Okay. Well, now we just do the integral. So first integrate with respect to y. y squared over 2 plus 2x squared y. Evaluate it between y equals, the y equals is optional here, but it helps to remind yourself that we're substituting this for y and not for x, right? And okay. No, there's no room over here. Doing more with that integral, so I have to work backwards. So this equals the integral from 1 minus square root of 45 1 plus square root of 45 of 16 minus x squared quantity squared. Be a little bit long. This minus this over 2. In other words, what we get for this term, upper limit minus lower limit, right? And then this, and that's going to be a 2x squared. So I'm going to have to graph this integral at the top. That'll be plus 2x squared, right? Times y 16. Well, 16 minus x squared minus 5 minus x. All this with respect to x. Now, it's a little bit of calculation, but no big deal. It's just going to be a fourth degree polynomial. It's easy to integrate. X to the fourth terms. This is going to give you x to the fourth over 2, right? And this is going to give you negative 2x to the fourth. Okay? You're going to have a negative 3/2 x to the fourth. I'm probably going to mess up something like that. But there it is. I write this out for you. Okay, x cubed. You're not going to get an x cubed term off of this or this. The only x cubed term you're going to get is from this x and this x squared, right? So you're going to have minus plus 2x cubed. X squared term. When you square this, you're going to get a 32x squared, right? And when you square this, you're going to get an x squared, and it's going to be minus. You're going to have 31x squared over 2. That's a 31/2 x squared. And keep that in mind. Now down here, I could have simplified this with 16 minus 5 is 11. There's our 11 again. That's going to mess us up. I'm going to mess it up. Okay, but 11 and times 2x squared is 22x squared. So you have 22x squared plus 31/2 x squared. And that's 44 and 31, 73/2 x squared. Now again, if you're doing this, simplify this, multiply everything up, be careful, and then collect your terms. And I'm just investigating the whole thing to find out where we're going to get x squared, where we're going to get x cubed. It's kind of, that could be handy to do whatever you think you can do securely. Okay, then we've got to have x's, and we're going to have a negative 10x here. But there's a negative on it, so it's a 10x, and 10x over 2 is a 5x. So we're not going to get anything below an x squared out of this thing. So I think we have a 5x. And then we have a minus 25 over half, 2 minus 25 halves. So we want to evaluate that between the limits we have integrated together, right? So this becomes, it's going to be x to the fifth over 5, so it's going to be negative 3x to the fifth over 10. X to the fourth over 2 is going to give us 1/2 x to the fourth. X squared, x cubed over 3 is going to give us 73 over 6 x squared. 5x, going to give us 5/2 x squared. That's 3x cubed. 5/2 x squared minus 25 halves x. I'm going to go ahead and show off and show that I can integrate a constant. Okay? Since I showed before that. Okay. The minus 1 minus the square root of 45 over 2. 1 plus the square root of 45 over 2. Now I'm going to get really sloppy and I'm going to approximate this as 4. I'm going to approximate this as negative 3. Because I don't want to do that much arithmetic with higher powers. Q was pushing it. I could do it, but it wouldn't be pretty, and it wouldn't be as fast as the live class. Okay. So if I have 4 up here, 4 to the 5th, everybody knows is 1024. Okay. It's the same as 2 to the 10th, right? That's a standard thing everybody needs to know. Powers of 2 up to the 10th power at least. So that's like 1,000 over 10 is 100. Times negative 3 is negative 3. And then x to the 4 is going to be 256. That's going to be 128. It's not going to be terribly accurate because this is like 3.8 and not 4. The 1024 is going to be reduced quite a bit. So it's 128. Now, as you get to the lower powers, it gets less and less serious, but it stays pretty serious up to at least 2. Okay. 64 here, 6 into 64 is about 11. 11 times 72 is about 800. Five halves x squared is 5 halves of 16 is about 40. And that's going to be minus. Then minus what you get when you do this at negative 3. Negative 3, you got to be careful about the signs. So 3 to the 5th, I got to think for a minute. That's 81, 343. 3, 9, 27, 81, 342, 242. Okay. Let's track with the power of that book. 343 times 3 is about 1,000 over 10. That's about 100, and it's negative because it's taking an odd power of a negative number, right? And I realized that if anybody is looking at this on the video, I'm not going to see it. Okay, so all we're doing, we've written out the integral. Okay, we've just substituted the limits here to get all this. And then we went through these expressions, picked out everything that gives an x to the fourth, an x cubed, an x squared, an x. But normally you just go ahead and expand all these and try to pick out. Okay. Hopefully this is what you get. So that we take the antiderivatives. Antiderivative x to the fourth is x to the fifth over 5. Negative 3 halves gives us negative 3 tenths x to the fifth. And so forth. Just straightforward integration. Now we're just approximating this as 4 and approximating this as 3, negative 3. Okay. So if you take the fourth power of negative 3, it's only 81. And half of that is 40. If you cube negative 3, you get negative 27. So that's like negative 27 over 6 is like 4.5. 4.5 times 73 is roughly 300. Okay. And then x squared would be about 9. 5 halves of 9 is about 20. It's 22.5. I'm not being precise enough to worry about that 2.5. And then it's going to be minus 25 halves of 3, which is like minus 4. I predicted that the total density ought to be between 750 and 1,000. Okay, and certainly between 500 and 1,500. Okay, that's negative. Okay, negative 300 and negative 50 is negative 350. This is about 760. Okay, so that's about 4 tenths. Uh-oh. So we have minus 100, but we got plus 300. That's going to work out. Okay. I need to have any more dead space. Okay, one alert person in the room has informed me. There's only one other person in this. It isn't big. That should be a negative 300 because we're cubing a negative 3. Negative 3. So that makes all this negative, so that's going to help. Okay, so we have like negative 400 here, right? And then we have only plus, well, and negative 440, and only plus a 60, so that's 380. And voila, that's 700. Okay. So we spent a lot of time on that, and I do a lot of arithmetic in my head, which isn't necessarily going to be everybody's skill set. Okay. I used to be really good at it. I'm still fairly okay at it, but I make too many mistakes. So it's become pretty unreliable. But it is helpful to be making these estimates, to compare the estimates with your results. So this is a reasonable estimate. I still don't like my area calculation, but I do like this, okay? So I think this might be fairly close. Now, remember, we've rounded up 3.85 up to 4 and a negative 2.85 to a negative 3, right? And that's going to have some effect. So I just won't guarantee that this is in my original estimate between 750 and 1,000. So these numbers are going to get smaller, but so are these. These numbers are going to get bigger. And since some of the important ones are negative, I actually think it's going to come out a little less than 7. If you want to take your machine and check my results, that'll corroborate them. And if they're reasonably consistent, you can kind of believe that you did the machine right. And you can kind of believe that I did at least most of this right. Okay. So ultimately, as an engineer, you believe your machine, but depending on your situation, you want to have the ability to do a common sense estimate. And the machine that doesn't have any common sense. Okay? Ways to leverage common sense with your machine as well. So take that for what it's worth. Okay, so what we've done here, again, our density function was this. So we took the typical increment, we found that the mass of the increment was this. Okay? And that's a typical increment within our partition. You have to understand that partition. I gave you vertical strips and all that name partition rows. So you have a picture of what you're doing. The total mass then, you just sum it all up and it approaches an integral in a very straightforward manner. You know, the theory of how it approaches is quite straightforward. So you want to get as much of that as you can, but there it is. So then we just, here it is. And the rest of it is just performing the integral and doing a lot of incorrect arithmetic. Okay. So what did we end up with? We ended up with total mass, right? And a couple of question marks there because it's an approximation. Okay. Okay, well, now we want to go on and do moment of inertia. Okay. And we want to do moment of inertia about some axis. Well, the most convenient axis to use would be the y-axis. So now remember that your moment of inertia per particle. And of course, we just did this in physics yesterday, and everybody here is in physics. So particle I equals mr squared, where m's a mass, and r is a distance from the axis, right? Okay. Consider mass in each increment be a particle. Typical increment. Typical increment. has moment of inertia. You won't believe it, we're almost done. Okay, moment of, except I'm not going to do an estimate. I'm not going to estimate all the arithmetic. The typical increment has moment of inertia. Now I'm going to do this delta, capital I for moment of inertia, sub ij equal I've got the right expression. So going to be the density function, right? Okay, one thing is, how far is this mass from the ij increment with sample point xi star, yj star? How far is that from the y-axis? If this is the increment with an xi star and a yj star, how far is it from the y-axis? Discuss that for just a minute. We're almost out of time, but I'm going to pause and discuss it. Okay, well, first we have to establish how far this typical increment is from the y-axis, but it's clear that that distance is just xi star. Okay, how far it is. So we multiply the distance from the axis, which is r, but here it's, we'll throw the r squared on the m. The mass is yj star plus 2xi star squared times delta xi delta yj, right? That's the mass, that's your m, and your r is your distance from the axis of rotation, which is the y-axis in this case, and that's going to be xi star squared. Integral will then be the integral from that 1 minus the square root, I get tired of writing this down. 1 minus the square root of 45 over 2 to 1 plus square root of 45. Chalk is doing real well there. Or let's say that I'm not doing real well with chalk. It's a responsibility where it belongs. Okay, but we understand what I'm writing here. We can't really read it. And then the integral from 5 minus x, 16 minus x squared of the limiting expression here, which is going to be x squared y plus 2x to the 4th dy dx. In other words, identical to our density integral, but with the x squared in there because that's how far each point is from the y-axis. And that's what gives us moment of inertia. And of course, you understand the kinetic energy connection and all that stuff. Because that's exactly what you're beating your head over in physics right now. Okay? So, what's that going to end up? I'm not going to try to estimate it. You're going to have an x squared times every term. So you're going to end up with an x to the 7th over 14 here, an x to the 6th over 3, and so forth. Okay. In other words, every term here is going to be multiplied by x squared. So we do the add derivatives, you're going to get the associated stuff, but it's going to be exactly like this, but just with different numbers and different powers. So it's going to be very straightforward to do that, even if it's a little tedious, especially if you're trying to do it mentally. And I just feel like so on the studio, but yeah, again, you got that x squared in there. So every term here, well, you're going to have x squared times all this, right? You can have an x squared in there, you have the y squared, the 2x to the fourth, which we just wrote down in the moment of inertia calculation. Okay. And that's going to go through all the way to here. So when you integrate every term, it's going to have power 2 higher than it does. And that's just straightforward. I'm not even going to attempt to estimate what that'll come out. I mean, I can kind of estimate what I think the moment of inertia would be, because intuitively, I'll do that just to have something entertaining and work it out and see. Okay, so if the total mass here is 790, because of the way everything works, of course, we can visualize this as a surface in 3 dimensions. And you might think of that, you know, your density would be your function out here. The total mass would be the area under that curve. That's pretty much what we just calculated. Your area under that surface is all here. Okay. Now the surface changes when you multiply everything by x squared, but just visualizing that surface, okay, kind of like this, goes from being about an average of maybe 11 units high above this strip to an average of 30 units high here. So I'm thinking radius of vibration might be, and we'll talk about that later, it might be about 2.5. And if all the mass is concentrated 2.5 units from here, then your MR squared would be 790 times 2.5 squared. It's about 6, so it's about 5,000. Okay. So I'm guessing that interval will come out around 5,000 just based on physical intuition. And I think physical intuition is shaky even with somebody who's much better at it than I am. Okay. But I'm not bad at that. Okay. Usually. Sometimes, of course, I'm just out in left field, right? But if you get something between 3,000 and 7,000, that would indicate my estimate, okay, and my intuition. So, I ask you just work that out. You use your calculator if you want to do the interval, because you've seen how to do these intervals, at least one of them by hand. But just to verify, try to do that area, write it out, do it. Sometimes before next class, if you get a chance. And then if you want to put the moment of inertia integral into the machine, it's just tedious. You don't learn anything new by doing that integration. And you're just integrating a polynomial, so you don't need more practice integrating polynomials. Okay. See what it would do. And then you could even think about how you would integrate this if you partition the y-axis from whatever the y-coordinate is here up to 6 points. Okay? You'd have 2 regions. You'd have to do this region here because above this level, you're going from here to here. You're going from the parabola to the parabola. Below this interval, you're doing from a straight line to the parabola. Okay. And you could also think about, well, what's the moment of inertia about the x-axis? Okay, and I'll even make a guess at that. Let's see, average distance is 10. Vibration stuff. You have in the ballpark of 100 pounds. I'm guessing. Okay. You want to check me using your machine? That would not be a bad exercise. Okay. Don't feel obligated, but might be interesting.
Recording in progress.
Okay. We have a situation here where X is a number of widgets, and a widget is just something it's an object that has to be manufactured and sold, okay? So, as I said earlier, it could be shirts, could be automobile, could be cameras, okay? But the number of widgets. And Y is going to be the cost to manufacture, okay? Now, task is going to be, based on this, estimate the coordinates of 2 points on the straight line and get the equation of the line. Okay? So, an estimate was made. Now, if you're watching this video, you should make your own estimates. Okay? Try to get the equation of the line. Don't wait for me to tell you. Just do it. And then if you get stuck, well, that's what we're doing here. We're getting unstuck. Stop at this point and do this. Don't just sit back and watch. Okay, so the estimate made, pretty reasonable estimate, was 1,250 here and 50,000 here. And then the estimate was made, well, this point corresponds to the 5,000 and the 100,000, which is a pretty reasonable estimate. So we have this point and this point. Next thing to do, and then if you have the estimates, don't know what to do next. Okay. You want to find the equation of the line with these 2 points. So you write out 2 points. So find the line. Through the points 1250. You should actually write this out, because what you've done in estimating these 2 points is you've given yourself the information you need to find the equation of the line. You should know, of course, that if you have the coordinates of 2 points on the line, there are methods to find the equation, and presumably if you're in section 2.3, which is what we're talking about, you've done 2.1 and 2.2, and you know what those methods are. Okay. So if you don't know those methods, well, a good start would be, and again, you should, if you haven't written this out, you ought to write it out and think about what we can do to get the equation of the line through the 2 points. We have formulas. And you got a formula for point slope. You got a formula for 2 points. Okay. And you can use those formulas to get the equation of the line. I think it's helpful to understand what the slope of this line. And that's going to be very helpful in finding the equation. I'm going to draw this triangle here. This side is the run, this leg is the run, this leg is the rise. This leg is parallel to the x-axis, this leg is parallel to the y-axis. And we think of going from one point to the other. I'm going to put little arrows on these sides of the triangle to indicate which point we want to start at and which point we want to end at. So this path here takes us from this point to this point, and this direct line here takes us from this point to this point. The run between these points is approaching 1250 to 5,000. That's $5,000 minus 1,250 equals 3,750. Divide. You're going from 50,000 up to 100,000. And even if you know darn well that that result is going to be 50,000, it's good to write it out to remind yourself of what to do when it's not obvious. So rise is 50,000. So the slope equals let's write out slope. Slope is not just a formula. Slope is rise divided by run. If you just use a formula blindly, you don't necessarily get that connection. And I think when I looked at your estimates, I said it was 4/3. I wasn't looking at all the zeros, it's 40 thirds. Okay, so slope's about 13.3. And I like to, you don't have to do this if it's not in my class. The calculus class. I put the 13.3 here next to the hypotenuse with a rectangle around it. And that's just a visual indication for me that the slope of this thing is 13.3. So I don't have to look back at a bunch of calculations to find my slope. So first find the slope. We did that up here. You'll say slope is 13.3. Okay, now what can you do? We have the coordinates of a couple points and a slope. What does it take to get the equation in a straight line? Well, one point and the slope is sufficient to get the equation. So if a point slope form is I minus y1 equals m times x minus x1. You could use the coordinates of either of these points for the x1 and the y1. And m is your slope, and you've already got that. Okay, so go ahead and do that if you wish. I'm going to go ahead. There's one connection here that I want to make. This is equivalent to saying that m equals x minus x1 over y minus y1. Okay. For every xy on the line. It's the meaning of this thing. It's just related to the formula for slope. Okay. In any case, there's enough information here. We have 2 points. We could use either one of them along with the slope, plug it in and solve for y. So we should do that at this point. I don't know if I was recording before or what. So there's a lot of dead space in this thing. Okay. Anyhow. Using y1 and x1 equal to 100,000 and 5,000 corresponding to this point, we plug in those numbers for x1 and y1, and we do the arithmetic. We add 100,000 to both sides, and we multiply through by 13.3, and here's what we get. And then we do the arithmetic on these 2 numbers, and we get this. So y is 13.3x plus 33,500. So now we can ask a few questions about this model. First of all, our model becomes do it round off. Class got something a little different. 32.7 or something like that. But remember, this number was rounded off from 40/3. And that makes a difference. There might be a little difference in calculation. Okay. So anyhow, there's a model. And if you're looking at the video, you can't see what I just wrote. Here's our model. So what's the what's a y-intercept? What does it mean? You want to think about that? Okay. And what's the cost to manufacture 4,000 widgets? Second question. How many can we manufacture for $65,000? All that information is there in this model and on this graph. So what I would recommend doing is, first of all, answer this question, try to figure out what the y-intercept means, but then estimate based on the graph. What's the cost to manufacture 4,000 widgets? How many can you manufacture for 65 grand? See if you look at the graph and answer those questions, and then see if you can use the equation and answer the question. So instruction here. Estimate from the graph. Then calculate from the equation. What are these questions? Okay, so we want to know the y-intercept, what it means. And we want to maybe, you know, said estimate these from the graph. Let's estimate the y-intercept from the graph. Okay, well, if that's 50,000, what's that look like? That looks like 47,000. About 40,000. Okay. So the y-intercept. Occurs at the point 0, 40,000, right? Now, so now from the equation, the y-intercept occurs when x is 0. If x is 0, y would be 37 or 33,500. Now, what's the meaning of the y-intercept? So the point 0, 40,000 would indicate, well, x is 0 and y is 40,000, right? And x is 0, what's the meaning of x again? X is your number of widgets, right? So 0 widgets cost $40,000. According to the equation, 0 widgets, you plug in 0 for x and you get 33,500, right? So, you know, the graph was based on estimates. And that 40,000 is based on an estimate. So these two don't agree real well, but they're in the right ballpark, okay? So it's a reasonable estimate. We have something like a reasonable equation. Now, in reality, your manufacturer would know what the fixed costs are, which is a cost to just get set up and start without even producing any widgets. And that's what you get when you produce 0 widgets, okay? It's basically saying it costs 40,000 or by the equation $33,500 to produce, to get set up before you can start producing widgets. Okay, well, that's an important thing to understand. Now, again, by estimates from the graph and then from the equation, what's the cost to manufacture 4,000 widgets and how many can be manufactured for $65,000? Okay. To manufacture 4,000 widgets, fairly straightforward. You find 4,000 here, come up here, over here. Get an estimate which might be 80,000. So maybe $80,000. Okay. So and how much can we manufacture for 65,000? Well, you find 65,000. Here, come over, put this down, and this adds about 2,000 just on my graph. Okay. We've got 4,500. That's also good. We'll see. Okay. So the estimate. Now, using the equation, okay. Left-handed, like Steve. Really thought I was going to go in. Okay. X equals 4,000. Okay, and that's going to be 40,000 plus 15. Kind of close to 83,000. I'm going to worry about arithmetic, but that's how you do it. You just plug it and work it out. I know pretty close to the 80,000 yes, that I estimate. Okay, and your estimate also came out pretty good. Okay, so yep. If we've got $65,000, that's our value of Y. So if Y equals $65,000 is 13.3x plus 33,500. Okay. We solve this for x. Subtract 33,500 from both sides. And this is the 13.3x equals 65,000 minus 33,500. And that's 31,500. So your solution will be x equals and camera. Okay. Now, a lot of that was written down below where you can see. Why 65,000? Well, there's our equation. Substitute 65,000, get this. Then you just solve this equation for x. And it'll tell you how many you can manufacture for $65,000. Okay. To solve, we subtract 33,500 from both sides. It'll go away from this side. It'll appear minus on this side. And that gives you 13.3x is 31,500. So there it is again. And to get x, we just divide both sides by 13.3. And it's going to be approximately $2,400. Okay. Now you estimated 2,500. I estimated 2,000. You're way better at this than I am. Okay. So that was very good. But you do